Hi everybody. Today what we're going to go through is a complete review of rotation angles from your grade 11 year. So we're going to cover a ton of material on this. I'm going to move through relatively quickly, but we need to review some terminology. Then we need to kind of make the transition a little bit over to radians as opposed to degrees. And then we're going to walk through and we're going to deal with solving for some exact values of trig ratios and then working backwards and solving some trig equations. So, as a very quick review of our rotation angles, we should all be good coming out of grade 11 that we know that we can rotate any angle we wish if we view it as the rotation around a set of axes. And so, I'm going to form my angle at the origin. And if I start in standard position, then my initial arm is going to lie on the positive x-axis. As I then rotate, the arm that rotates, and maybe it finishes in this position, would be referred to as the terminal arm. And as it rotates, it would then create an angle. Theta in this position would then be deemed to be what's called the principal angle. And so we could rotate our terminal arm any number of radians, and maybe if we were to rotate it into the second quadrant, then this would be theta. That would be the principal angle, the angle that I was rotating my terminal arm. We should also be good then that any principal angle can also create a related acute angle. And so if I was to label this angle that's formed between the terminal arm and the x-axis as alpha, alpha would be referred to as the related acute angle. And quite often you'll see that as like a short form as RAA. Now, we should also be good that you can rotate in any direction. And so rather than rotating in that positive direction, we could also rotate the other way to get to that same position. As we work our way through all those rotations, we should be good that I can rotate into any of my quadrants in any direction to have a terminal arm lie in any position. And so let's just take that last example then, and maybe I'll call that last angle beta. That I could then state that beta and theta are coterminal angles because they're angles that finish the terminal arm in the same position. So I don't know really how much else we need to review about rotation angles. Everything we need is kind of in there, as long as we also know that we could rotate more than a full rotation. So with that in our back pocket, what we're going to do is we're going to start to then work through some problems that will deal with some rotation angles. Let's put that in our back pocket for a second, and let's jump into another area of review from last year, special triangles. So what you'll see on the screen right now are two special angles for us last year. Now, this is going to be one of the only times that I'm going to talk in degrees moving forward. However, we should be good that in the instance of these special triangles, that my pi by 4 would be the same thing as a 45-degree angle, and my pi by 6 would be the same thing as a 30-degree angle. And we should all be good then on how those side lengths would have to compare. So all I'm going to do is I'm going to get rid of that degree measurement so that we can really get used to working in radians. So if I know that I have a pi by 4 angle, that is me taking a pi by 2 angle and cutting it in half. And if I cut it in half, that's me finding the diagonal of a square, which means that this side and this side must be equal. And so if those are equal, then let's use the easiest number to work with for a side length, which would be a length of 1. So if we called each of those a length of 1, then you could use Pythagorean theorem to find out the length of the hypotenuse. We can jump to that very quickly. There's my root 2. So hopefully we've got a little bit that we know for a pi by 4 angle, 45 degrees from last year, that your side lengths would be in the ratio 1, 1, and root 2. You want to have that special triangle in your back pocket. We're going to need it. Now, let's take a look at our next special triangle. This is our pi by 6. And so what we would normally do is we'd play around on our calculator a little bit, and I would ask you to punch into your calculator what the sine of pi by 6 was. Some of you will already know what that is. That you're going to end up seeing that the sine of pi by 6 is exactly a half. And so, if we were to calculate sine, we know sine is opposite over hypotenuse, then why don't we just make that the opposite over the hypotenuse and label those sides as 1 and 2? We could then go through and use Pythagorean theorem to find the length of the third side, being root 3. And so we should have from last year that a pi by 6, last year that was 30 degrees, would be a special triangle with side lengths 1, root 3, and 2. Now, some people come out of the grade 11 course kind of thinking of 3 special angles, and I would hope that really what we think of is 2 special triangles, of which a special angle is also incorporated. Because in that triangle, if I know that one of those angles is pi by 6, then I also know that the other angle would have to be a pi by 3. And again, one of the last times I'm going to use degrees, if there was a 30 in there, inside that right triangle, then the other angle had to be a 60 degree. And so, because you know that one special triangle, you actually know the set of sides for the other. That would end up being 1, root 3, and 2. So you want to have all of those in your back pocket because you will be asked a number of times to come up with something like a sine of pi by 4. And we need to be able to work through that triangle and say that that's opposite over hypotenuse. If I was to ask you what the tan of pi by 4 was, then you need to be able to go, that's opposite over adjacent. Those are both the same, 1. And same thing with pi by 6 and pi by 3. So that was a very quick review of those triangles. I'm going to work my way through a process where you don't have to memorize as much stuff as what you may think, especially when it comes to working with your 1, root 3, and 2 special triangle. So let's jump in and get some practice where we can see where we can apply this stuff. So what you'll see on the screen right now then is there is a situation where I am asking you to find the exact value of each ratio. What that means is that I would expect you to be able to solve all of these problems where you can get an exact, and we're going to also deal with some situations where you can't, but any situation where you can, without a calculator. So let's walk our way through the first one, sine of pi by 3. Okay, for me to be able to solve it, rotation angles can be very useful. So I'm going to put on a quick set of axes. I now have to rotate pi by 3. So I take a look and I say there's pi, and I'm dividing it by 3 parts. That means that I'm going to have a big angle sitting in here. I will have rotated pi by 3. We could now go through and drop in our height, because to come up with our ratio, we need to consider a triangle. Here's where we notice that we have a special angle, and therefore we can label the sides of that triangle in exact terms. So how do I think then about that pi by 3? Well, I'm taking pi by 3 and I am dividing it by the smallest number. My 3 angles for special angles are pi by 3, pi by 4, and pi by 6. And so if I'm taking pi and I'm dividing it by the smallest number, then it must create the biggest angle. And so, what is the opposite side then of a big angle? It has to be a big side. And so I know that that opposite side would have to be a root 3. Well, now that I have that side, I can fill in the rest of the sides of my triangle. I know that my adjacent side would be a 1 and my hypotenuse would be a 2 because the 2 is the longest length. Now that I have my triangle labeled, I can calculate my sine ratio. My sine ratio is opposite over adjacent, and so therefore I have over hypotenuse, and there we go. So rotation angles can be super useful as long as we have our special angles in our back pocket. I just walked through a way where we can build our special triangles. So other than remembering what the 3 sides are, we'll work on a process so that you can build where those side lengths go. Let's jump in and take a look at B. So when we start off with B, I'm going to deal with a rotation angle, put a quick set of axes down. I now have to rotate sine of 4 pi by 3. So I know that all the way around to my negative x-axis is pi. So what you'll really notice is that this actually becomes a little bit easier to work with radians. I'm just going to get rid of that green because that was only pi that I rotated. What I need to rotate is actually 4/3 of pi. So I'm going to focus in on the 4/3 part. That means that I need to rotate 1 and another third. That because I use radian measure, one of the benefits to that is it actually tells you what your related acute angle is. I already know that it's pi by 3. Okay, I can drop in my height and now label the sides of my triangle. Pi by 3 is a special angle, so I know my sides. It is the biggest special angle, so it must have the biggest opposite side. That means that my other sides are 1 and 2, and I can build my triangle. Now, what you'll notice is if I jump to that point, I have to show an awful lot of discipline right now, because the one part that I've omitted from my diagram is any direction. Don't forget that this opposite side was going down, so it needed to be negative. And this adjacent side was going left, so it needed to be negative. Now my diagram is proper, and now I can state the value of the sine ratio, which is opposite over hypotenuse. So there is us working our way through some rotation angles to find exact values of ratios, and we're also working with it in terms of radians. So let's keep going with problems like this. Let's take a look then at part C. The cos of 5 pi by 6. So we go through and we now have our rotation angle. So let's put on a quick set of axes and we're going to rotate 5 pi by 6. Notice I need to rotate 5/6 of pi. That means that when I rotate, I'm going to be a little bit short of pi. And again, my radian measure is already giving me my related acute angle. That if I rotated 5/6, I must have been 1/6 short of pi. Now I can drop in and I can label my sides. Pi by 6, I'm taking pi and I'm dividing it by 6. I'm dividing it by the biggest number, which means this must be the smallest special angle. The smallest special angle has the smallest opposite side. And if that side is 1, then my other sides must be root 3 and 2. I don't forget about my directions. I went to the left, therefore my adjacent side is negative. And now all I have to do is calculate my cos. My cos is adjacent over hypotenuse, so negative root 3 over 2. So as soon as you feel comfortable working through, I want you to pause the video and see if we match up in the end. So let's take a look at D together. Pause it if you need to. Okay, so I'm dealing with my rotation angle. I need to rotate 3 pi by 4. So I need to rotate 3/4, which puts my terminal arm here. There's my rotation. That tells me that I must be 1/4 short of pi, or a pi by 4. I can then drop in my height. I know that the sides of my pi by 4 have to be equal length, which makes my hypotenuse √2, and I don't forget about my directions. And so for me to then calculate the tan of that, just please don't write this, that we're going to simplify that, and you're just going to state -1. So hopefully we matched up. If not, hopefully we feel a little more confident moving forward. Let's keep going at this pace. Okay, I think E is a good opportunity for everyone to pause the video, see if we match up. So, quick set of axes. Okay, I do notice that I'm rotating in a negative direction. So now when I begin to rotate, I've got to go in this direction. I'm rotating 5/3. So this would be me rotating 3/3, because there's my -1. I then have to rotate another 2/3, which is going to put me here. That makes that my terminal arm. And it tells me that if I just rotated 2/3, I must be 1/3 short of my x-axis. Now, quick little thing for us to be able to check on. You know that anytime you rotate a full rotation, that you just rotated 2 pi. So if I was 1 pi by 3 short, then that would be with a common denominator 6 pi thirds minus pi thirds, which is going to give me my 5 pi by 3. Quick little check. I'm good. Let me get rid of that then, and we should be good to then finish off the problem. So I can drop in my height. Pi by 3 is my biggest angle, so I have my biggest opposite side. Fill in the rest. I'm in quadrant 1. I don't really have to worry about directional symbols. I can then state my cos, which is adjacent over hypotenuse. And so, as I said earlier, hopefully we match up and we're feeling comfortable getting back into the swing of things with rotation angles. Now what you're going to see on the screen is we're going to take the opposite direction to something. So what I want you to notice when you read the instructions for problem 2, that we're going to say that our angle theta lies between 0 and 2 pi, inclusive, and I'd like you to find the measures of theta if certain circumstances exist. So the big thing that we should notice is the last bunch of problems, you knew the angle. You rotated a certain angle. This is now asking you to go backwards and find the angle. So one quick thing as we begin. I think you're in the best position you can be in if when you read this problem and you see this restriction, that we no longer read it as theta must be greater than or equal to 0, less than or equal. We don't read the notation, but instead we interpret it. That what that notation is saying is one positive rotation. And so if I was to reread that problem, what it says is, if I have one positive rotation, find the measure or measures of theta if. The more we can start looking at that restriction in terms of rotations, the better off we'll be when we problem solve. So let's take a look at A. I want to walk my way through an A because since I have rotations, I can always use rotation angles. However, I want to maybe address something depending on kind of your background with this, and the way that we may view this problem. There is an acronym that allows people to go through and determine the placement of a terminal arm based on the sign of any trig ratio. And some of you may have in your background that acronym of CAST. That is, that you would even look at it and say, oh, well, I'll just use the CAST rule to figure out where I go. I am not the biggest fan of CAST rule. I think it has some rules to it. It also has ways that you apply it that are going to require you to find negatives or use special cases. And I think what I would like to do is I would like to try to make you a little bit better with it. So you are not going to hear me ever use the term CAST rule for us, other than to denote a couple things today. That what I think we should do is use our grade 10 knowledge of SOHCAHTOA and our grade 9 knowledge, let's say, of integers and plotting points. That you don't need a new rule to be able to solve any of these trig equations. Instead, you already have all that material in your background. So let's walk through it really quickly. This problem says that your sine ratio is positive. And you should be able to tell me where your terminal arm is simply by looking at your sine being positive. Because in grade 10, you learned SOHCAHTOA. And SOHCAHTOA is going to tell you that your sine ratio is opposite over hypotenuse. Now, we know that any time we label a hypotenuse, that it always has to be positive. Diagonals don't have direction symbols. However, horizontal movements do, as well as vertical movements. And so if I know then that this is a sine ratio and my hypotenuse is always positive, then the only thing I have to think about is my opposite side being positive. Opposite is vertical. So if I was to ask you, where is your vertical side positive? Then you should pretty comfortably say quadrant 1 or quadrant 2. That's where we go up, and up is positive. And so using that reasoning, I can already go straight to where my two terminal arms could be. Well, now I can work my way through backwards. I can drop in my height. And since I've been given that sine is 1/2 and sine is opposite over hypotenuse, I can label the sides of my triangle. Opposite hypotenuse. Now, you never, ever, ever have to put on this red dimension, the fact that the adjacent side is √3 or negative √3. Never needed. But some people like it. What putting on those side links allows us to do is to then say, I know what my related acute angle is. That if I have a really small opposite side, it must come from a small angle. Therefore, pi/6 is my related acute angle. Therefore, pi/6 is my related acute angle. And if that's the case, then we can state what our principal angle would be. Well, our quadrant 1 answer is nice and easy. We would have to rotate pi/6. And my quadrant 2 answer is also relatively easy because I would have to rotate all the way to pi, but be 1/6 short. So 5pi/6. Notice we do not have to worry about negative angles or angles that are greater than one rotation because of the restriction put on our original statement. There you go. Now, I already know that I'm going to have some people who are holding on to CAST rule because you have it from grade 11. And I'm going to challenge you that as we work and we move our way forward, we're going to start to get a lot faster if you can leave CAST rule behind. A couple quick things to note then, to be faster this year than what we were last year. My sine of any angle is really my opposite side, since, as we said, my hypotenuse never changes. My cos, well, cos is adjacent over hypotenuse. And since my hypotenuse never changes signs, I don't have to worry about it. My cos is my adjacent. The only time that I have to consider both portions of my ratio is when I deal with a tan. Tan is opposite over adjacent, and both of those signs could change. So the only thing I need there is plotting points and dealing with maybe some grade 7 integers. That in this case, if I had tan that was a positive, then that tells me that my fraction has to have top and bottom being the same signs. If my tan was negative, then the only way I can make a fraction be a negative is if I had different signs. And we can determine our quadrants in that case. We're going to see this in practice, and we're going to see why we can be a lot faster if we just use our old reasoning. So let's jump in and work through a bunch of problems like these. Okay, the first case, and this will be one of the last two times that I mentioned cast rule. Question B, cos theta equals negative 1 over root 2. So for any cast rule stubborn holdouts, you guys take a look at that and you say, hey, my cos is negative. Well, cast rule always tells me when my ratio is positive. So for me to have to solve this problem, I actually have to think of the anti-case, the opposite case. I would argue to you, in a lot of cases, it's faster just to go and find what you need. So, as I begin this problem, I note that my cos is negative. Cos is negative. Well, how do I calculate cos? Cos is adjacent over hypotenuse. So, where is my adjacent side negative? And we should be good that that means to the left. Well, now that we have our terminal arms there, the rest really becomes easy. Drop in your height, label your sides. Cos gave me adjacent, so my adjacent side is 1, my hypotenuse is root 2. Again, we never have to label the opposite side, but some of us might. And that should really bring home that our related acute angles are pi by 4. So, what does that do for my solution? Well, if my related acute angle is pi by 4, then my quadrant 2 solution would have to be a quarter short of 1. So 3/4, or 3 pi by 4. My quadrant 3 solution would have to be 1 plus an additional quarter, or 5/4, 5 pi by 4. There we go. Nice and fast. Okay, same thing as what we said before. As soon as you are ready to give it a shot on your own, start pausing the video and seeing if we match up. So let's take a look at C. So as we take a look at C, I have my rotation angle. So there's my set of axes. My sine is positive. And so since my sine is positive, sine is opposite. Opposite is positive when I go up. Now that I have that, drop in your height. Sine is opposite over hypotenuse. I can then tell that my related acute angle, since I have a big opposite side, has to be my biggest angle. And so if I had to state my solution then, I would be pi by 3 in the first quadrant, or 2 pi by 3 in the second quadrant, 1/3 short of 1. Hopefully we matched up, and hopefully we're feeling a little more comfortable with it. Let's keep it going. And so what you see on the screen now, problem D. Tan of theta equals -1 over root 3. Okay, my quick set of axes. My tan is negative. Tan doesn't have the hypotenuse in it, so I have to consider both top and bottom. That means in my fraction, since it's negative, the top and the bottom have to be opposite signs. So how can I get opposite signs as I move on my axes? Well, I either move to the right and down, that puts me into quadrant 4, or I move to the left and up, which puts me into quadrant 2. Now I can drop in my heights, and I can label the sides of my triangle. Quadrant 4, it is opposite over adjacent. Quadrant 2, it is opposite over adjacent. That should allow me then to say smallest opposite side means smallest related acute angle. And therefore, my actual solution for theta then would be in quadrant 2, I'm 1/6 short of 1. And in quadrant 4, I'm 1/6 short of 2 pi. So if I was to take 2 and I thought about it in sixths, then that would be 12 pi by 6. And so since I'm 1 pi by 6, or 1/6 short of the 12 sixths, then there's my 11 pi by 6. Okay, that gets us to the end of a certain type of problem, and now I'd like everybody to take a look at E. I'm going to shrink down that screen a little bit, just so we can work our way through E, because for some of us, we may notice pretty quickly, E's a little different. So we take a look at E, and you now have the sign being -5/13. Well, we can start off this problem exactly the same as we always have. My sign is negative. Sign is opposite, so if the opposite is negative, then I must be going down. Okay, I can now drop in my heights. But as I go to label my opposite side and my hypotenuse, then we may pretty quickly realize that we're not dealing with a special angle. Okay, all that means then is all we can talk about are approximates. So that means you're going to need your calculator. So pop out your calculator, and what we're going to do is we're going to work our way through, and we're going to solve using an approximate. So the first thing I'd like you to notice is you've done this an awful lot. However, you didn't always do it this way. That you've often used your inverse to be able to go backwards and find an angle, except there's a key component here. When you went through and you said that the sign was negative and therefore your terminal arms went into quadrant 3 and quadrant 4, you've used up the negative. The negative told you the direction. What you're looking for is the size of the angle. So we often denote related acute angles with something like alpha. So alpha would then equal the inverse sine of +5/13. I don't use the negative. The negative was used to put on the blue terminal arms. Therefore, I need the number portion to tell me the size of the angle. And so if I pretty quickly go through and I take my inverse sine and I use exact values, 5 divided by 13, then my related acute angle is going to give me something like 0.39 radians. And so what we do is we'll round it off to 2 decimal places. Now I want you to notice one other issue. We're going to have to make sure our calculator is in radian mode. So what you just came up with then was that this is approximately 0.39 and this is approximately 0.39. And so therefore, if you were to solve then for, well, what is theta, which is what the problem asked, then to get into quadrant 3, you would be pi plus that approximate. Or to get into fourth quadrant, you would be 2 pi, the full rotation, minus that angle. Now, we can simplify that to a different approximate. Use 3.14 if you wish as your decimal approximate to be able to work your way through. In this instance, it won't have any bearing. However, when we do get into problem solving, you're going to want to use your pi button on here to be as exact as what you can be. And what we end up getting down to are those two angles. So, should make sense a little bit. To get into quadrant 3, you're a little bit more than pi. To get into quadrant 4, you're a little bit less than 2 pi. And there's our two approximates. And so, if it's not a special triangle, then we can't use exact values. It means we need to use approximates using our calculator. So I'd like you to take a look at F then, and I'd like everybody to pause the video at this point, go through, solve the problem on your own, and let's use this one as kind of a last chance to match up on a situation like this. So go ahead and pause and begin now. Okay, we should be back. So if I have my rotation angle, I now have my cos being negative. So if cos is negative and cos is adjacent, then adjacent is negative, so I am left. Now I can drop in. My adjacent side would then have to be negative 7, and my hypotenuse would have to be 11. In that instance, then, I could go through and find that other side, but I don't need it. As long as I say that my related acute angle is the inverse cos of positive 7/11. So again, make sure your calculator is in radian mode. That should get us down to an approximate radian measure of 0.88 rads. If that's the case, then I know that this is my related acute angle, and therefore to solve for theta means that I am pi minus my 0.88, or I am pi plus my 0.88. So quadrant 2 or quadrant 3 solution. Now go ahead, sub in your pi, and make sure that you then calculate for an approximate. So to get into quadrant 2, we would be approximately 2.26 rads, or to get into quadrant 3, we would be approximately 4.02 rads. So that should just give us a little something extra to make sure that we're good with dealing with when can we have exact values, when do we need to deal with approximates. Okay, I want to jump into one other thing from review, and then I think we should have everything that we need moving forward. For some of us, one of the areas that we maybe struggled with in grade 11 was dealing with angles on an axis. And so, as we started to rotate, if our terminal arm finished with our angle on an axis, then what ended up happening was we would go through and we would maybe have to deal with a special circumstance, and it was maybe a little confusing, or definitely we were less confident with it. So what I want to kind of walk through is maybe a quick case for us to be able to go through and solve. So the first thing that we need to address is, for instance, what would happen if I rotated 0 or 2 pi in terms of rads? That when we went through, what we end up having is no triangle that we could construct. My terminal arm is lying directly on top of my initial arm. So what we can often do then is imagine that that terminal arm was lying in that position. If we imagine that it was in the blue position, then we could drop down a height and construct a triangle. Now, one way that people work through this sort of thing is they start to ask themselves the question, what side does not exist in the triangle? And if you can answer that question, then you really become efficient on dealing with angles on an axis. So if my blue terminal arm should really be lying in the red position, then I really have no green side. I have no opposite side. Therefore, my opposite side has a length of 0. And since my red arm is the same as my blue arm, then I end up using 1s to denote both of those side lengths. So, in a weird way, you can often say that we actually construct a two-sided triangle. That then allows you to go through and say that, well, the sine of 0, sine's opposite. If I'm at an angle of 0, I have no opposite side. So my sine is 0. If I have no opposite side, then that means my adjacent side is everything. And mathematically, everything is 1. My tan of 0, well, if I have no opposite side, then I'm taking 0 and I'm dividing it, therefore it's 0. That we have the means to be able to work through and come up with those those ratios pretty quickly. So let's take a look then on what happens if we were to rotate pi by 2. So if we were to rotate pi by 2, then that would put our terminal arm directly on our positive y-axis. We get into the same trouble again. We can't construct a triangle. So what we can imagine is we tip that terminal arm a little bit past, and so we think about it in the blue position. That allows us to drop in a height, but now we ask ourselves that green question again. That if the blue arm is really vertical, then which side doesn't exist? And if my terminal arm is vertical, then I have no adjacent side. Which means that the other sides of my triangle are 1s, are everything. That's what allows me then to say that the sine of pi by 2 is opposite over hypotenuse. If I answer the green question, then the sine of being vertical, opposite vertical, since there is no adjacent side, my opposite side is everything, so 1. My cos of pi by 2, which side doesn't exist? The adjacent, cos is adjacent, so it's 0. And when I calculate the tan of pi by 2, I now need opposite over adjacent. I am dividing by 0. That makes that undefined. And so we would have the means to be able to rotate all the way around. So in a lot of cases, if we can think about it that way, then let's think about it that way. So what if I rotated pi? Well, to construct that triangle, which side doesn't exist? Since I'm entirely across, then that means there is no opposite side. So the opposite side is 0. So, since sine is opposite, then the sine of pi is 0. Since the opposite side is 0, then my adjacent side is everything, so 1. The only thing I have to remember is I went to the left, so it was a negative 1. My tan is opposite over adjacent. There's my 0. We take a look. If I was to rotate 3 pi by 2, so now I'm on the negative y-axis, which side doesn't exist if I'm vertical? My horizontal side. So my adjacent side is nothing. Therefore, the sine of 3 pi by 2, since sine is the other, it has to be 1. I just have to remember that I'm going down, so my opposite side is negative. My cos of 3 pi by 2, well, cos is adjacent, and since adjacent side is 0, and my tan of 3 pi by 2 is asking me to take my opposite side and divide it by 0, therefore I am undefined. Some of you may like working their way through those imaginary triangles in a way, but they're going to be a lot faster to deal with in the future if we start to think about what side doesn't exist on a triangle. So let's try to use that as we move forward. And now what we'll come to is one of the other reasons, and this is the last time I'm going to mention cast rule, and that why I consider cast rule to be lacking in some areas. If we were going to work our way through and deal with sine theta equaling 0, then cast rule would say put the terminal arm where your sine is 0. Well, 0 is neither positive nor negative. And so since I don't have a sine to apply to my sine ratio, I can kind of stumble my way through what quadrants to put that in. Where instead, if I just think about what are the key components of sine. Sine is opposite. So my opposite side must be 0. Opposite is vertical. That means that I do not go up or down anything. Well, the only place my terminal arm can lie in if I don't go up or down anything means directly across. And therefore, theta has to give me 0 where I started, or pi on my negative x-axis. Now, just don't forget about also including 2 pi, that I could have went all the way around again, since that was included in our restriction. Now let's take a look at h, and we're going to see how we get really, really fast with this. Okay, cos theta equals 0. Well, cos is adjacent. So I need to address, where is my adjacent side 0? Adjacent means go across. So if I don't go across any, if my across value is 0, then I must be completely vertical. Therefore, theta's got to put me at pi by 2 for the positive y-axis or 3 pi by 2 for the negative y-axis. We can get a lot faster if we start to think about what sides don't exist in dealing with our imaginary triangles. And so if we finish off on our last 2 problems then, I think we should be good. Cos theta equals 1. And so if I was to go through and try to solve that problem, then maybe I'm really, really aware. And I say, well, I recognize that what cos theta equaling 1 means is that cos equals everything. And so cos is adjacent. So where does my adjacent side become everything? If I'm directly across. Now, you may also have thought, yeah, but this would be directly across as well. But you have to be very careful. Because that would be me going directly across, but in the negative direction. And notice that my cos ratio is positive in the problem. So if I avoid the negative trap, then therefore theta could be 0 or 2 pi. Now, I also want to maybe walk through this one with the complete blinders on, so you can see that using your application of SOHCAHTOA and coordinates, you could actually stumble on this pretty quickly. Let's say I went right back to the very beginning and we addressed this with the blinders on. And I said, well, cos is positive. Cos is adjacent. So where is my adjacent positive? To the right. And maybe I thought of both quadrants. Well, now when I go through to label my triangles, I can think of it as a fraction, so I can think of it as 1 over 1. That means that my adjacent side is 1 and my hypotenuse is 1. Pythagorean theorem would then say that my third side must be 0. And so if my third side is 0, my vertical side is 0, then I can't go up or down at all. I must be directly across. So, 2 different ways to be able to get to us being able to solve for the correct angle. Okay, pause the video, give Jay a shot. Okay, and we should be back, so we're able to work our way through J. So, we've got a quick set of axes. We take a look at that, and we see that tan theta is equal to 0. So in our head, we're saying to ourselves, tan is opposite over adjacent. So if opposite over adjacent equals 0, then my opposite side is 0. So where's my opposite 0? Straight across. And so therefore, theta is going to be 0 or pi or 2 pi. Just make one important note on the distinction between I and j. For anybody who was like, yeah, but wait a second, why are you able to go to the left? The left would be a negative. Yes, just keep in mind though, that would still be a 0 opposite side divided by a -1 adjacent side, which is still 0. In the previous case, we would have had a negative adjacent side divided by a positive hypotenuse, which would have changed the sign of that ratio. So today we did a full review of grade 11 stuff, all of our rotation angles, being able to work backwards to solve trig equations, and we did it all using radians. Okay, your job now, jump in and get as much practice as you can. Good luck.